Okay, so today we're going to talk about information cascades, as the title slide tells us, and we'll start with a little bit of following the crowd, shall we? So pictured here is one of my favorite baseball players and philosophers, Yogi Berra, and he's quite famous for his sayings. He was once asked whether he wanted to have dinner at a highly regarded New York restaurant, and he replied with a remark that kind of combined wisdom and contradiction. He said, "Nobody goes there anymore. It's too crowded." When people are connected, they can actually influence one another, and individual behavior will give way to collective outcomes in a variety of different areas. If you're watching the news about social media, you may see that in opinions, politics, or if you're a fan of marketing, you may see that in products. Just as an example, outside of the world of social media, you might choose a restaurant in a new town that you haven't tried. And maybe base that a little bit on Yelp reviews. Restaurant A is your original choice, but when you go there, there's nobody there. Meanwhile, restaurant B across the street is competition, and there's a line out the door. Do you change your decision based on the fact that everybody's going to restaurant B? So a lot of times we'll actually trust the wisdom of the crowd there and join in, even if it means disregarding our own information. That's known as herding or an information cascade. And the author is saying information cascade has potential to occur when people make decisions sequentially, with later people watching the actions of earlier people, and from these actions inferring something about what the earlier people know. Hey, maybe they know that's a good restaurant. We should follow them in there. It's not necessarily a mindless thing that's going on, but rather it's drawing rational inferences from limited information. We haven't eaten at the restaurant. We just know what the Yelp reviews say, but we also know the behavior of the people in that town that are going into that restaurant. So, this can, be maybe conformity is, you get a large crowd size. People want to do, what's popular or cool, but it can also be due to collective information, like top selling books or top selling albums. Hey, everybody's reading this. Maybe I should take a look at it. Might have something to say. Informational effects versus direct benefit effects. We're going to talk about the informational effects today, and then in a later chapter, we're going to talk about direct benefit effects. But direct benefit effect is if you want to copy the behavior of others, if there's a direct benefit to you from aligning your behavior with their behavior. So, for example, adopting a technology platform for compatibility in the book oddly uses the example of a fax machine. It was out of date, probably when the book was written, but if you think back to the early fax machines, well, somebody else had to have it in order for you to really want it. If nobody else has a fax machine, there's no point in having one other than, I guess to have it if you're a collector of old equipment or something. But basically you would have it in order to communicate with others, or, if there was a direct benefit involved, you could fax invoices, which was actually quite common back in the 80s and 90s. I remember faxing my homework in graduate school at one point, in an early thing of distance learning. So let's talk about a simple experiment, and just to show this information cascade. We basically have these ingredients. There's some decision to be made. It could be whether to adopt a new technology, eat in a new restaurant. It could be any type of decision. And people are going to make this decision sequentially. So person one decides, and person two sees what they decided. Person three sees what they decided. Person four sees what all three of them decided. Each person has some private information, like, for example, in the restaurant, those Yelp reviews, that helps guide their decision, but they also have the information that's conveyed by the previous people in the experiment making their choices and what their choices are. So, you can't directly observe the private information that they have. Where did they get their reviews? But you can make inferences about this private information from what they do. So the experiment the book talks about takes place in a large group of students in a classroom. The experimenter puts an urn, a container, in front of the room with 3 marbles hidden in it, so you can't see it, it's not transparent. there's a 50% chance that it contains 2 red marbles and 1 blue marble. That's a majority red urn. And a 50% chance that it's a majority blue urn that contains 2 blue marbles and 1 red marble. One by one, each student comes up to the front of the room, draws a marble, looks at the color, doesn't show it, and then places it back in the urn without showing the rest of the class. The student needs to guess whether the urn is majority red or majority blue, and they publicly announce their guess to the class. We assume at the very end of the experiment, each student who has guessed correctly receives some type of reward. You know, it could be bonus points. The book suggests monetary rewards, but that's not in keeping in line with current budgets, while students who guessed incorrectly receive nothing. The public announcement of what you guess is a key component of this. The students who have not yet had their turn don't get to see which colors we drew, but they do get to hear the guesses as they're being made. So it's similar to the restaurant. You don't know the reviews the other people read, but you know what decision they made. So how does this work as a line of reasoning? Well, the first student should follow a simple decision rule for making a guess. If he or she picks a red marble, then it's better to guess the urn is majority red, because there's a 2/3 chance that you're getting a red marble if it's majority red. If you see a blue marble, it's better to guess that the urn is majority blue. So the student's answer will convey perfect information about what they have seen. The second student should also guess the color that they've seen. You know, you can reason with it as if you got to draw it twice from the urn. Now, it's definitely easier if you got the same color as the first student. If the colors are different, then break the tie by guessing the color that that's the second student saw. Now, if the first 2 students have guessed opposite colors, say one says red, one says blue, then the third student should just guess the color that he sees. That'll effectively break the tie between the 2 guesses. If the first 2 guesses were the same, for example, both were blue, and the student drew a different color, then it would be like you drew 3 and you saw 2 of them blue and 1 red, which would lead you to believe that it was majority blue. So you should guess blue and ignore your own private information. So more generally, when the first 2 guesses are the same, the third student should guess that color as well, regardless of which color he or she drew from the urn. And that's the beginning of this information cascade. And the rest of it will follow. Information cascades, under right conditions, cascades can easily occur. They can lead to non-optimal outcomes. So suppose we have a majority red urn. There's a 1/3 chance the first student draws a blue ball, and a 1/3 chance the second student draws a blue ball. Multiply those together, and you get 1 out of 9 chance. The first 2 draws being blue, even though it's a red majority urn. So 1/9 of the time, you get the first 2 would be blue, and the third student draws a red ball. But according to the line of reasoning, the third student should ignore what he or she sees and go with that blue guess, because it's like they saw 2/3 of them being a majority. Now, and that'll cascade through the rest of it, because we know only the first 2 are revealing information that they saw. Now, you can break information cascades by revealing additional information. So suppose that we get to students 50 and 51, they both draw red marbles, even though we're guessing it was majority blue, and they reveal that red marble to the rest of the class. We now have 4 pieces of information: 2 draws that were, we know were blue, 1 and 2, and 2 that we know were red, which were 50 and 51. And then, so if we're student number 52, we should guess what we see. But that's a way to stop an information cascade, and they can actually be fragile. So how can we model this? Well, a tool that we can use is something called Bayes' rule, and that deals with conditional probability. So we're going to build a mathematical model of our experiment. We need a little help from this Bayes' rule. So consider in probability theory, we say probability of A is the probability that event A occurs. We could assign that some probability, say P. And we can also think about another event, B. And in the picture, you have the world view of this with the universe being the enclosed box. A event is the first circle, B event is the second circle, and both A and B occurring is the intersection of them. A or B would be the contents of both circles, or A union B. So the probability of A, given that another event B has occurred, is the probability of A intersect B divided by the probability of B. And Bayes' rule takes that and uses probability of B given A, which is going to be the same probability of A intersect B divided by the probability of A, to give us the probability of A given B is probability of A times the probability of B given A divided by the probability of B. So we can rewrite that intersection in a different way to give Bayes' rule. Here A is called the prior probability, and probability of A given B is called the posterior probability. You can see an example of Bayes' rule in witness testimony, and that's actually quite common. The book gives an example of a witness seeing a yellow taxi in a city with black and yellow taxi cabs. Black taxi cabs make up 80% of the fleet in the city, and 20% of them are yellow taxi cabs. The witnesses have 80% accuracy. Bayes' rule shows that the fact that it would be a yellow taxi cab, given that the person saw a yellow taxi cab, is only 50% likely under those conditions. So another example deals with spam filtering. If you want to take a look at that, it's pretty interesting and applicable. It's also used in baseball. You know, the probability of a hit, given that there are two people on base, sometimes they'll actually announce that. The baseball is all about the statistics. And of course, the most famous example is the Monty Hall or let's make a deal problem. So let's make a deal problem, sometimes known as the Monty Hall problem. So there was a game show called Let's Make a Deal. Suppose you were on that show. The host would give you a choice of 3 doors. So you could pick, say, door number 1. Behind one door is a car, and behind the other 2 are goats. So you pick a door, say I pick number 1, and the host, who knows what's behind the doors, opens another door, say number 3, which has a goat. He says, do you want to switch over to door number 2? Is it to your advantage to switch your choice? Well, it actually is. You should definitely switch, since the original answer, door number 1, only had a 1/3 chance, and there was a 2/3 chance of it being behind either door number 2 or door number 3. And so by switching over to door number 2, it would be like you were picking both door 2 and 3 in the original problem. And this was written up in a column by a columnist by the name of Marilyn Vos-Savant, who claimed to have the highest IQ in the world. And she wrote this up, of course, with the correct answer. But there was a lot of criticism from pretty smart people who didn't quite get Bayes' rule. So here's one: you blew it, and you blew it big. Since you seem to have difficulty grasping the basic principle of work here, I'll explain. After the host reveals a goat, you now have a 1 in 2 chance of being correct. Whether you change your selection or not, the odds are the same. There's enough mathematical literacy in this country, and we don't need the world's highest IQ propagating more. Shame. And that was from a professor at the University of Florida. It turned out he was wrong in that case. And ultimately, the way that people actually accepted this was they had a solution that consisted of kindergartners replicating the experiment with cups and shells, and showed that you were better off 2/3 of the time to switch. They also did an analysis of every time the problem played out on television, showed that 2/3 of the time, you would benefit from switching. So there are a couple of empirical pieces of evidence that led people to ultimately accept it, even though they didn't completely get Bayes there. So back to our herding experiment. Each student's decision is intrinsically based on determining a conditional probability. So they're trying to estimate the conditional probability that the urn is majority blue or majority red, given what they've seen and heard. So, they see the marble and they hear the previous guesses. Now, to maximize the chance of winning that reward, say the extra credit points. You should guess majority blue if the probability of majority blue given what you've seen and heard is greater than 1/2. And it's the same calculation for red. The probability that the majority of it is red, given what you've seen and heard, is greater than 1/2, then you should guess red. We also know that the probability that the majority of them are red is 1/2 because one urn is 2/3 red balls and 1/3 blue ball. The probability that the majority is blue is 1/2 because the other urn is a blue majority urn. Probability of blue given a majority blue urn is 2/3 because 2/3 of the balls in the blue majority urn are blue. Probability of red given a red majority urn is also 2/3. So what the first student wants to know is the probability of the majority being blue given that it was blue is equal to the probability of the majority being blue times the probability of blue given the majority blue divided by the probability of blue. Basically, we take that first conditional probability, use Bayes' rule. And then we know those values from the previous slide. We have 1/2 times 2/3. Probability that you have the majority blue urn is 1/2 because there are only 2 urns. Probability of blue given that it was given a majority blue urn is 2/3, and the probability of blue, here we take all the balls together, a total of 6 balls. 3 of them will be blue and 3 of them will be red, so that's equal to 1/2, and we get 2/3. So, probability of it being a majority blues, assuming that you saw blue, is 2/3. Similar calculation for the second student. Now, for the third student, things get a bit tricky. Here we might have the probability of blue given that the first 2 were blue and you saw red. Again, we can use Bayes' rule to calculate that and we get 2/3. So you should still guess blue even though you saw red. And there's where you get the information cascade. So in general, Bayes' rule can help us understand general information cascades. In making a model, we need to assume there are a group of people who are going to make decisions sequentially, one after another. 2 ingredients, or 3 ingredients. There's the state of the world. There are 2 possible outcomes. A good idea, hey, that restaurant's going to be good with probability P, or a bad idea with probability 1 minus P. Wasn't what I was expecting. If we reject an option presented to us, we get 0. So if somebody says, hey, you should try that restaurant, no, I don't get anything for rejecting it. Assuming that we got something that was a good restaurant, then VG is the payoff for good. That will be positive. VB is the payoff for bad, and that's negative, because you paid for food and it wasn't very good. And we say, basically, we say that they sum to 0. So before you get any information, the expected payout is neutral. And we also have signals. High signal suggests that it was a good outcome. Hey, I really like this place. You should give it a try. Or low suggests a bad outcome. It was not that good. If accepting is a good idea, then we're going to get more high than low signals. And this actually works out for the marbles example. So as a result, individuals should accept the option when they get more high signals than low signals, and reject it when they get more low than high. They're indifferent when they get the same number of each. In other words, in the simple setting with the sequence of signals, they can decide according to majority vote over the signals that they receive. So in this setup, you have your own private signal. Those in the restaurant would be the Yelp reviews that you read, and in the marbles game, the marble that you drew out and actually got to see. You don't get to see the private signals of any other earlier people. You don't get to see what people drew out of that urn or what reviews they read for the restaurant. Person 1 is going to follow their own private signal because there's no other information available. Person 2 will get person 1 signal, and they'll have their own private signal, but they should follow their own private signal. Person 3 now has 3 signals. If 1 and 2 are the same, follow the crowd. If 1 and 2 are different, then person 3 gets to use their own private signal. And a cascade will begin when the number of acceptances and rejections, the difference between them reaches 2. And a cascade is when no individual's decision can be influenced by their own signal. So consider person number n. If the acceptances are equal to the rejections, then use your own signal. If the accept minus reject, the absolute difference of that is less than or equal to 1, which covers the earlier case, use your own signal. If it's greater than or equal to 2, then you follow the majority, and that's what happened with our marbles. And it's really hard for this difference to stay in that range of -1 to 1 for a prolonged period of time. If we get 3 of the same signal in a row, then we end up with a cascade, because we go from -1 all the way to +2, or from +1 all the way down to -2. As the number of people goes to infinity, the probability of information cascade goes to 1. So this is a simple model, and you may not see all the previous decisions that were made. Hey, maybe you come to class late and you don't see what people drew out of the, or what decisions were announced when people made their draws from the urn. Or, you may show up to the restaurant at 7 p.m. and you didn't see all the people going into restaurant A at 4 p.m. So, and not all private signals convey equal information. Some people have better access to information than others. If you're local to a place and that that's a good restaurant, regardless of the, Yelp reviews that they're a little bit off, then, you have access to that private information. That's a private signal that's more valuable. Cascades can be wrong, as we saw in the case where we had a 1/9 probability of drawing 2 blue balls in a majority red urn. And they're based on very little information. That cascade with the marbles started with just 2 pieces of information in most cases. They're also fragile if someone has additional private signals, like the 2 students 50 and 51 showing the red balls, making that public. Then we can stop the cascade. There are some implications for it. Of course, marketers can take advantage of cascades by getting early adopters, and committees can actually fall prey to that. Say you're selecting a candidate for a position on the hiring committee. You ask the first person, they say, hey, candidate A is the best person. Ask the next one, candidate A is the best person. People may start questioning, hey, I picked candidate B. Was there something I didn't see? So that's not to say that you may be thinking, well, gosh, man, I should never follow the crowd, or be careful about making decisions based on crowds. And that's sometimes true, but if everyone's guessing independently and it's not sequential, then there's some wisdom in the crowd that can often lead to the correct answer. There's a book called The Wisdom of Crowds by James Surowiecki, and it gives examples about guessing the number of jelly beans in a jar, guessing the weight of a prize bull, and actually the guesses in the crowd, if you take the mean of them, they conform to nearly the number of jelly beans or nearly the weight of the prize bull. So there is some wisdom in asking the crowd independently, not necessarily sequentially. And this is a worthwhile read as a book. And that's it for today.